So I've been involved in the last few years, actually just the last year and a half really, on this new topic to me for my research, and that is connecting what's going on in the Arctic, which you've already seen a bit of, and the big changes happening there, and the fact that it's connecting up to the weather pattern changes that we're seeing here in the mid-latitudes. I've been doing this work with my colleague Steve Vavris at the University of Wisconsin. So I want to start by just reviewing a few more of the extreme events that we've seen just in the last couple years around the northern hemisphere. And Mother Nature has dished up one heck of a smorgasbord. Just this past winter, this is up near my hometown up in Massachusetts, we were battered by nor'easter after nor'easter this winter. In the UK, they've had a heck of a couple of summers, springs, and winters with a drought one minute and then a flood the next. In Alaska last summer, they had the worst flooding in southeast Alaska they've ever had. In Central Europe, as Stu already mentioned, just this past week, they've had some of the worst flooding they've ever had. Last summer in Greenland, you don't usually think of Greenland and flooding in the same thought, but they had the worst flooding they've ever had in Greenland. And of course, the last few winters in Europe have been exceptionally severe, not just in the usual places, but they got snow all the way down to the Black Sea and the north coast of the Mediterranean, or the north coast of Africa, actually, so the south coast, actually. And then in Central Europe, the residents there were very upset by all the snow they got. And then over in Japan, it's just, you can't even imagine the snowplow that they must have used to cut that road. And then, of course, there's been the heat waves. And this picture wouldn't be so unusual, except this was Burlington, Vermont in March, 2 Marches ago. And then, of course, last summer we had some horrific heat waves in our country, which left Texas marinas high and dry, and Eurasia's had their own set of heat waves and droughts to deal with. So the question is, and Stu's already alluded to this, what the heck is going on? And really the question that everybody's really asking is, are we having something to do with this incredible increase in extreme weather that everybody's been noticing now? And you know, it's really only been the last few years where scientists have been able or been willing to step up and answer this question. And now more and more, after we've had a flurry of studies looking into this very linkage, more and more of us are willing to stand up and say, yes, indeed, there is a link between climate change and extreme weather. I like to start by putting this whole situation in context and remind you of the really horrible pickle we've gotten ourselves into. So you've probably seen a graph like this at some point where we're looking at the curve of temperature going back about 430,000 years, the red line, along with the amount of carbon dioxide in the atmosphere, the blue line. And you can see back in time, with time going back to the left, that they worked in pretty close step with each other. And in fact, the temperature oscillations were really due to changes in the Earth's orbit, and the CO2 followed the temperature. But over on the right there, you'll see that something really different's going on. And here's our carbon dioxide levels today. We've recently broken through the 400 parts per million record, which is not a good thing. But what you see is you look at comparing what the carbon dioxide levels are now and what the temperature of the Earth is doing, and you can see they're completely out of whack with each other. We put this carbon dioxide into the atmosphere so fast that the Earth's climate system has not been able to catch up yet. It takes a long time. And it also takes a long time for that carbon dioxide to leave the atmosphere, even if we were able to stop producing it today. So we've got a lot of climate change coming our way, even if we were able to stop producing carbon dioxide and other greenhouse gases. And we also know that the last time CO2 levels were as high as they are now, the globe was several degrees warmer. Now remember, we've only increased the globe's temperature by about 1 degree so far, centigrade. So we've got several more degrees. The sea levels were tens of feet higher, and humans weren't even around then. This was at least probably more like 2.5 million years ago, but at least 800,000 years ago. It's a real pickle. But the Earth's temperature is starting to catch up. And as we look back to the late 1800s, we see that we're on track to increase the globe's temperatures increasing. In fact, 10 of the 11 warmest years on record have occurred since 1998. And what I really want to talk about is the fact that it's not warming everywhere at the same amount. It's warming much faster in the Arctic, as you can see from this plot of temperature anomalies or differences from normal for the last decade or so. And you can see those red colors up in the northern part of the graph are showing that it's warmed much, much faster than the global average up in the Arctic. So this is what we call Arctic amplification. This is another way to look at it, where we can look how temperature has changed in different latitude slices of the Earth. The light blue line is for the Arctic, and you can see that it's varied a lot more than all the other parts of the globe. And you can focus in on the green line too. That's for the northern mid-latitudes. That's where we all live. And so what you see is that the light blue line and the green line have been getting farther and farther apart as the Arctic has warmed much faster than the rest of the globe. The fact that the Arctic's temperature time series has fluctuated so much more shows you how sensitive the Arctic is to the global temperature change. So when the globe was cooler than normal, the Arctic was a lot cooler than normal. So it has a much larger response to global temperature changes. In fact, we know now that the Arctic today is it's warming 2 to 3 times faster than the rest of the northern hemisphere. And this is due to a number of things. It's due to the loss of Arctic sea ice, which you've heard about a little, and we're going to talk about more. It's also caused by the loss of snow in the spring on high latitude land areas. So right now, as a matter of fact, this last month of May has seen the lowest levels of snow cover, especially in Eurasia, but also in the northern North America, than we've ever had. And this has been a very steady trend downward. In fact, the snow has been disappearing in the spring faster than the sea ice has been disappearing, which is saying something. And this is important, especially as we go into summer here, because as we lose that snow on high latitude land, then it exposes the soil underneath it earlier to the strong sunshine, which allows it to warm up, and it gives the continents an earlier start to the heating season. So we're setting ourselves up for a higher likelihood of heat waves and droughts as we lose this snow earlier in the spring. The other factor that's affecting this Arctic amplification is the amount of water vapor is increasing in the atmosphere everywhere, but especially percentage-wise in the Arctic. And the water vapor not only is a greenhouse gas all by itself, but when it condenses into liquid in a cloud, it releases heat into the atmosphere. So that warms the atmosphere, and also we get more clouds forming. And clouds are very good at trapping heat down to the surface. So these are the main factors that are causing the Arctic to warm so fast. Now we can look at this by season too. And this is what I've plotted here, going back to the late 1940s or so. And each of these curves is showing how much warmer the Arctic is compared to the rest of the northern hemisphere. So what you see is that brown curve, which is over to the right there in present times, is showing that the Arctic amplification is largest in the fall. This makes sense because that's when the effects of the sea ice loss are most important. It's also big in the winter. That's mostly because of the water vapor increase, but also the residual effect of the sea ice loss. We're also seeing it starting to happen in the spring. And the spring goes back to that loss of snow that I told you about. And the summer, again, it's both the water vapor and the result of the snow loss. So we're seeing Arctic amplification happen not just in the fall and winter now, but in all seasons. But you'll notice it's a relatively recent signal. It only goes back a couple of decades. And that makes it hard to see how the effects are unfolding in terms of weather changes, because it's a relatively short signal. But they're starting to emerge. So let's take a little more look at the sea ice story here. And as you probably know, it's really a mere shadow of its former self. if we look back 30 years, look down on the North Pole, what the sea ice used to look like at the end of the summer when it's at its minimum extent, that pink stuff is all the sea ice, pretty much filling up the whole Arctic Ocean. But if we look at just what it looked like just this past summer, 2012, you can see with your eye that it's just terrifically diminished from what it was only back in 1980. In fact, the amount of sea ice covering the Arctic Ocean is about half of what it was only then. And then if we take into account the thickness of that ice and multiply it by the extent, we get the volume that Stu showed you, and the volume now is about 80% less than it was only 30 years ago. It's just amazing. So, and what's left is very broken, it's slushy, people describe it as very weak, and so it's very vulnerable to any anomalies in the winds or the ocean currents or whatever. And so it's a very different place than it used to be. And we can look back in time, actually, and ask, how unusual is this? Did this happen before? And we can look at sediment cores in the Arctic Ocean that tell us about how much sea ice there was even back 1,500 years. And you can see this squiggly line. Yes, it varies from year to year somewhat, but it's pretty steady until you look at the blue curve, which is the more modern record, and see how it drops off compared to the previous 1,500 years or so. But then if we put last summer on this plot, you can't. You need a whole new graph. Well, why do we care about the sea ice? Well, as you know, ice is very white, as is snow, and if you have only half as much ice, which is the 2012 is the white, the pink line is what it should be. We have much less ice than we used to have, and so the result is that when the ice is there, it reflects most of the sun's energy right back to outer space, so it never enters the climate system at all. But now, because we have so much less ice, a lot more of the sun's energy is going right into the Arctic Ocean. It's warming it up. And so by the time fall comes along, after all that heat from the sun and going into the ocean, all of that heat then has to be re-released into the atmosphere. This is what it looks like in the fall. So all that heat goes back into the atmosphere in the form of just regular sensible heat, water vapor, and also infrared radiation. And if you calculate how much heat went into the Arctic Ocean just last summer in the areas where there used to be ice, it's about enough energy to power the entire United States for 25 years. Okay, so what's this Arctic amplification stuff all about? Why should we care about the fact that the Arctic is warming so fast? Well, Stu did a great job of introducing this concept. So if we consider a layer of the atmosphere, he showed the 500 millibar surface. So we can think of it just of a layer of atmosphere, say extending from Washington, D.C. up to the Arctic. And we know that because it's warmer here, this layer is going to be thicker here in Washington, D.C. than it is up in the Arctic. So basically what that means is that it's forming a hill. It's thicker here than it is up in the north. And so the air wants to flow downhill, just like water wants to flow down the side of a mountain. And as it does so, because the Earth is spinning, instead of going just from the south to the north, it gets turned to the right. And this is what creates what we call the jet stream, which is this fast-moving river of air that basically encircles the northern hemisphere. So what's happening, though, is that because we're warming the Arctic more than we are down here, this hill is becoming less steep. And so the force on that air that's trying to flow northward is not as strong. And so the winds are also weaker. So the jet stream's west to east winds are weaker. So this is a different vision of that thickness of that layer, that 500 millibar layer. And looking down on the North Pole, the blue colors show us that it's thinner there and it gets thicker as you go out to the more southern latitudes. But now look at how the thickness of that layer has changed. Just in the last, this is just for the last decade or so. So this is actually showing the change in the thickness of that layer. And you can see that those red colors are where that layer has gotten much thicker and it's bullseyed right on top of the Arctic. So this is showing us again how the hill is becoming less steep. And it's this force that drives the winds, the west to east winds of the jet stream. So we can actually measure these winds in the real world and see how they've changed over the last several decades. And that's what's shown here. Going back to the late 1970s, the solid line is the speed of the west to east winds of the jet stream up at the 500 millibar level over time. And what you see is that they start to drop off about 10% slower since about the mid-1990s. And plotted on there in the dashed line is the extent of sea ice, just for comparison. And you see that they both tend to drop off right about at the same time. And we know that when the winds get weaker in the jet stream, with the west to east winds, that the trajectory that the jet stream takes around the northern hemisphere tends to take a wavier path. And you can think of a river flowing down a mountain. When that river is going down a steep mountainside, it tends to go quite directly. But when it gets out to the coastal plain and there's not much slope to the land, you've all seen those rivers that tend to take these big meandering paths. And that's similar to what happens to the jet stream when the winds get weak. So the other effect that we've identified, or first hypothesized, is that if we've got one of these waves in the jet stream, then if you warm the northern tips of these waves, which we call ridges, more than the southern parts, then those ridges should actually get stretched northward. And this is another effect that actually makes these waves larger. So there are two effects as a result of the warming being larger in the Arctic than it is in the areas farther south. But why do we care about these waves in the jet stream? Well, it turns out those waves control our weather. So here's a schematic of a typical jet stream, that orange line there, blowing from basically west to east, but with waves in it. And you can see that it separates the cold air to the north from the warm air to the south. It's the boundary. So if you're south of the jet stream, you're in the warm air. And as one of these waves goes by you, then you might go into the cold air. But the other thing is, these different areas of the waves where the winds are coming from the southwest are where you find the stormy patterns. It's where those storms tend to form as that wind brings the moisture up from the tropics. And then in the northwesterly flow of the waves is where you have dry, settled weather. You have high pressure and nice weather. So these waves have everything to do with the weather that we feel down here on the surface. So this is a very cool schematic that just came out last week. It was produced by John Garrett, and it was put on a wonderful summary of what jet streams are and why we care about them that was on the skepticalscience.org blog. And he produced this nice schematic that shows how when the waves are relatively small, in the upper panel there, they tend to move quite quickly from west to east. But when they get large, like in the lower panel, they tend to shift much more slowly. And why is that important? Well, now you know that there's certain kinds of weather associated with the different parts of those waves. So if you've got the waves that are shallow, then your weather is going to change frequently. But if the waves get big, then you're going to tend to get stuck in the same weather pattern for a much longer time. So now what I'm going to do is show you an actual jet stream from the real world. I've got to jump over here and click on this box. Okay, so this is an animation put together by NASA, and I'm not going to be able to control it for you, but what you're going to see first as we zoom down on the northern hemisphere here is the waves start out quite shallow, and if you look closely, they were moving quickly. But now the waves have gotten much bigger, and you can see that they tend to get stuck. We're forming a block up over Greenland, and there's another cutoff low. I'm going to play it one more time because it goes by so fast. So watch for the shallow waves in the beginning part and see how they move relatively quickly right across the North American continent. So right there, you can see them shifting quite quickly, and then the waves get much larger, and you can see that they tend to get stuck in place, and they even tend to form blocking patterns and cut off lows, just like Stu talked about. But you can see the real jet stream is quite a messy beast. Okay. All right, so that's the theory. So now let's look at some actual analysis that we've been doing to see if this idea is really showing up in the real world. So what we did was we actually looked at how these waves in the jet stream are changing their character. So here's just another way of plotting this thickness of the layer, the height of the layer that Stu showed, this 500 millibar height around the whole northern hemisphere. And what we did was we looked at how these peaks in these waves are changing over time, which is shown in this plot here as the trends in the frequency of these ridges according to longitude. So that plot matches the map up above it. So what you can see is that over on the right there where it's circled shows that the ridges are increasing quite dramatically, especially in the North Atlantic. But you'll see that almost everywhere, almost all longitudes, the numbers are positive. They're all above 0, which means that the trends are positive everywhere, ridges are increasing everywhere. So it matches up very well with what Stu just told you. We can also look at the size of the waves. And remember, we're expecting the waves to get larger. So as we plot how the trend in the size of the waves looks versus longitude, we can see that again, everywhere they're above, the values are above 0. And this is for fall only, by the way. So what we see is that the waves seem to be getting larger all across the northern hemisphere, just as we thought they would. We've also come up with a way to measure how wavy the upper level flow is. This is a harder thing to get to figure out, to measure sort of objectively, but we've come up with a relatively simple metric. And basically what it is just looking at how much of the wind is in the north-south direction versus the total wind. And so what this is showing is the trend in the waviness, if you will, of the winds at 500 millibars in the fall. So the blue colors are where it's less wavy, and the red colors are where it's more wavy. And what we find is that there's this big swath of areas starting from North America, across the North Atlantic, over into Europe and Eurasia, where the values are positive. The flow at 500 millibars is, in fact, getting wavier. And the reason it's set up the way this is across the northern hemisphere, if you go back to the changes in the thickness of this layer, it actually makes sense. So over in North America there, you can see that there's that tongue of warm, of extra thick air that extends southward over North America, exactly where we see the waviness increasing. But then it shifts northward as you go around through Europe and Asia, just as the trends in the waviness do too. So it seems to match up with where we're seeing this poleward hill getting shallower. Think back to that hill getting shallower. So we'll take a quick look at summer. And what we see in the summer, again, a very strong increase in the ridges over North America, over North Atlantic, and all the way over into Europe, and also in the North Pacific. So what this suggests is that we're getting a lot more of these ridges in these places, just as Stu showed. And you can think back to his plot of Hurricane Sandy. Okay, almost done. When there was a big ridge in place then, and also we see that there's, the waves are also getting larger, especially in the North Atlantic sector. So just to wrap up quickly, I'm going to look at a couple of particular extreme weather events, and we'll take a look at what the jet stream was doing during those extreme weather conditions. So think back to this past March, where it was quite cold in the east and warm in the west, compared to March of 2012, when we broke thousands of high temperature records during March all across the east. And here's what the jet stream looked like in those two Marches, only 1 year apart. In 2012, we had this big dip over the west, a big ridge over the east that stayed in place for a very long time. That's what, and again, a big amplified flow or big waves in the jet stream. But the next year, big waves in the jet stream, but they're just in a different place. So the same reason, but they're just set up in a different location. And if we look at a couple of other extreme events, those record snows in Alaska that I showed you, look what the jet stream was doing there. You can see Alaska's right up at the top there, with California sort of stretching down to the right, and the gray area is where the actual jet stream was. And what you see is that it's bringing all this moisture up from the central Pacific, but the cold air is over Alaska, and that's exactly the ingredient you need for a lot of snow. But that very amplified, very wavy pattern meant that that pattern was in place for a long time. Spain had some record flooding last September, and once again, Spain is over in the middle of the right side there. You can see the North America on the left, and again, the jet stream was in this very wavy pattern. So just a quick note about Sandy. Stu already covered it, but what we saw in place when Sandy came along, I mean, I'm sounding like a broken record here, but this big dip in the jet stream over the eastern half of the country, big ridge over the North Atlantic, causing that blocking high that brought Sandy right into New Jersey. And what we were seeing in the Arctic at that time, remember this is right after that record loss of snow, of sea ice in 2012, the Arctic was way warmer than normal. So the question is whether that extra warmth in the Arctic had a role in strengthening that block, maybe extending it farther northward or prolonging it. We're not sure, but it could have. And the other factors we need to keep in mind when we talk about Sandy is the oceans were much warmer all along the East Coast. Remember, Sandy came along the end of October, very late to be that far north. But the ocean off the East Coast was warmer than normal. And this is happening right now as well. We still see warm temperatures all along the eastern seaboard. And this may allow hurricane seasons to lengthen. Storms may be able to survive farther north, later in the season, where they can interact with big swings in the jet stream like this. So just finally, let's take a quick look at how this particular year of sea ice is unfolding. Starting with the ice extent. Remember, this is the area of ice. So starting in February, and the red dot is today. And what we see is the black line is where it should be, going back to, say, 1980, where I showed you in the beginning. The dashed line is what it did in 2012. And what you can see, the blue line, is this year. You can see that most of it, we've been actually below the amount of ice for last year, which blew the record away. So we're already in a bad spot. But then if we look at the sea ice thickness, and here we go from January right through the entire year, each of those lines is for a different year. And if you can see the numbers there, the red line on top is for 1980, and basically you're going through time closer and closer to present until you get to today. And here we are with our ice thickness today. So we're going into this summer with the least amount of ice we've ever had in terms of thickness for this date. So, remember the fiscal cliff? I mean, that was a few months ago, but there it is. And here we've got this other cliff coming our way, which is looking pretty daunting right now. But as Lou mentioned, there is a silver lining to all of this, I think, and that is that this extreme weather that's been affecting a lot of people personally in their wallet, in their families, in their homes, in their food prices, it's got people's attention. The public is starting to listen. The media is certainly starting to listen. Even a few politicians are starting to listen. And I think the good news is this anti-science bunker is really starting to crumble. And I think we have an incredible opportunity here to take advantage of what's a bad situation, but making headway into doing something about it. So thank you very much.